as Michal said, we will be discussing the second paper in the Learning to Rank series, right? So you guys will see that there's actually a third paper as well. And Jock actually posted that in Microsoft Teams. So you guys are welcome to check that out. But yeah, so the one we'll cover today is called Enhancing Cross-Sectional Currency Strategies, this time with a context-aware learning to rank model that actually incorporates self-attention, which is pretty cool. So it's from the Oxford Plan Research Group. So, okay, let's start. So I'm just going to give a quick overview of cross-sectional momentum strategies. So I think by now we know what that is, but I'll give a quick overview. And yeah, then we'll just check out learning to rank strategies again. So if you guys can remember from 2 weeks back, in the first paper, we covered most of that. And we'll then compare the original learning to rank strategies with their context-aware counterparts. Okay. And then we'll move over to simulation methodology. So same as before with the previous learning to rank paper, we'll look at the features that they added, the training period, currencies that they included, and so on. So for the third part, we'll look at the context-aware learning to rank model. And it's actually based on a transformer architecture, which is quite cool. And I'm going to break it down for us into 3 parts, which will hopefully make it easier to understand. And if we look at the results, so we're going to take our benchmark functions. So things like a multi-layer perceptron. We'll look at just randomly choosing stocks to long and shorts, for example. Yeah, and then we'll compare that to our learning to rank algorithms. And then we'll take those originals and we'll compare them to the context-aware learning to rank models. And then in the very end, we'll see if these context-aware learning to rank models can actually still give accurate rankings in normal and risk-off market states. So that will be the very last slide. Okay, cool. So what are cross-sectional momentum strategies? So we know that we can break cross-sectional momentum down into a time series part and then also a cross-sectional part. But this paper obviously focuses on cross-sectional strategies. And the only thing you really care about in this strategy is just the relative performance, right, of your assets. So, will these pairs of assets perform better than others? So it's not about the specific returns of each of the assets as such. And we saw with the previous learning to rank paper that you can actually rank your securities based on a specific scoring model, right? And because we're dealing with momentum, you can actually buy the top decile according to that, and then also short the bottom decile according to those rankings. And just an additional note, so you don't necessarily have to rank your assets according to momentum only. You can actually also use size and value if you want to. But yeah, this paper will obviously focus on momentum. But if you do find that interesting, you can always refer back to the very first paper. There's also a YouTube video on that one. Okay, cool. So learning to rank. So we saw before that this is a really powerful technique, right? And this paper utilizes it for currencies. And instead of a long rebalancing period, we actually rebalance the portfolio daily, which is quite interesting of this paper. And we're still going to use a scoring function to rank currency, so in exactly the same way as before. And we know that these methods include pointwise, pairwise, and also a listwise algorithm. And we saw that pointwise is sort of an inferior method. So this paper also just focuses on pairwise and listwise. And then in order to actually account for the context of a specific rank, right, we're going to use pairwise logistic loss and then also listnet loss. And this will plug into the transformer network. Okay. And the reason we do this is because we want to improve on the globally learned ranking functions. So this paper really highlights, the shortcomings thereof. The fact that it doesn't really take into account the differences between your feature distributions across the currencies. So this paper tries to improve by adding a specific function to the original function. And I'll show you guys what that looks like in just a bit. So yeah, the main idea is we have our original model, right? So things like a listnet or a lambda mart, right? We rank our currencies in this case, And then we use the context-aware model to actually refine those scores. And then we still select our top and our bottom decile, and then we construct our portfolio. Okay, cool. And for this next part, we're just going to break it down into the original learning to rank model and then also the context-aware learning to rank model. So you'll see that it closely follows one another, right? So we still have our scoring function, right? We have our data. We know that we get a specific score for each of the currencies, and then we need to sort those scores according to the momentum signal. And after we do that, we can just select our securities. So let's say, for example, we would only like the top 3 in the top decile, for example, then we select that, and then we construct our portfolio. Okay. And if we look at the loss function, so we can see that if we move from here to here, again, it's just adding something additional, right? So the original loss function is, again, just our ground truth. So in other words, the sorted decile labels, right, for the next period for each currency. And then this is just the function, and it includes just a vector of all of the currencies that we have. So I think in this paper, we have 31 currencies. Okay. And if we move from a traditional learning to rank model to the context-aware model, you'll see that we follow exactly the same process, right? And the output over here is just our scores for each of the currencies. And that actually serves as the input for our context-aware model. Okay, so what does this entail? So if we look at this loss function, we still have that ground truth, right? So the sorted decile labels for the next period, but then we also include an additional function. And this is actually a completely separate model that we also train separately. And then we use that pairwise and that listwise loss within the transformer network. And you'll see that in this loss function, we still include the output from the original model, right? So RT is just the sorted decile labels, right, from the previous output, and then XT is just the corresponding currencies for each. And that's just the previous or the original learning to rank function from before. So that one over there. Okay, and that's a basic difference, right? So we have a list of scores from our original learning to rank model, and we use the transformer network, the context-aware model, to actually just refine or re-rank those scores. And then we still need to select the securities, and then we still need to construct the portfolio. Okay. Cool. So if we look at the methodology, you guys will recognize this slide from 2 weeks ago. So it's very, very similar to... Oh, yes.
Can I just ask on the previous one? So they rank by the top decile. So they do it for the long positions only then. And then they have a separate loss function for the short positions as well, if I understand correct.
Yes, correct. And it's like very similar. Yes.
Yes, it's the same methodology. The one is just the top decile and the one is the bottom decile, but it's two separate loss functions.
Yes, exactly.
Okay.
And you plug those into the transformer network. Yes.
Okay, thanks.
Awesome. Cool. You guys are welcome to stop me at any time and ask a question. Like Michal did, no problem. Okay, cool. So as I said, the methodology closely follows that of the first paper. So we, instead of rebalancing over a long period, we actually rebalance daily. So that's quite interesting of this paper. We have 31 currencies in our universe, and we keep the volatility targeting at 15%. We still have the 33-day exponentially weighted standard deviation, and we don't include transaction costs. So if you are interested in including that, you can always refer back to the deep momentum network paper that we discussed. We also have a video on that. Welcome to go and check that out. Cool. So over here we have a function that's again, it should look familiar. So for the cross-sectional momentum, T to T1 again just refers to rebalancing daily. And then over here we still have our signal, right? So the momentum signal, if it's -1 for the currency, it will be in the bottom decile. If it's 1, it'll be in the top decile, and 0 otherwise. So, and then we divide by n. And again, we have the volatility targeting. So the annual volatility target divided by the current volatility. And then again, this is just the future returns of the currency. Cool. So that's that function. And we have data from 2000 to 2020, and we got that from the source. So this paper, it ranks the currencies, and then so it splits it into top decile, bottom decile, and then it just chooses to, or it uses the top 3 to long, and then the bottom 3 to short. So that's the process that they follow. And then the features that they include, so exactly the same as with our previous paper that we discussed. So you have raw returns, volatility scaled returns, so for those periods, and then volatility scaled MACD based indicators. Cool. So those make up the features. And we have a bit of a difference over here with the training. So they use something called optimization, but they still keep those 5-year periods for training. And then they also use a 90-10 training and test split. Cool. And then the learning to rank benchmarks. So these also should look familiar from the previous paper. So the pairwise logistic regression, they use list MLE, list net, and then lambda mart. So if you guys can remember from the previous session, lambda mart outperformed all of the rest, right? And we'll see kind of a similar trend in this paper as well. Cool. So for the context-aware learning to rank model, so as I said before, it's based on a transformer architecture, and I'll try to break it down into 3 separate parts. So we'll first look at positional encodings. It uses self-attention mechanisms, so based on multi-heads, and then we're also going to stack our encoded layers. Okay, so what does that look like? So this is just, I would say, like a base model for a transformer. So we have inputs, we have an encoder block, we have 2 levels, so multi-head attention, we have a feed-forward network, and then this is called an encoder-decoder block. We have our softmax function, and this just outputs the scores that we're looking for. Okay, so what's the goal of the transformer? So we basically just want to learn a context-aware scoring function, right? Because if we have our scores from the original model, we can actually just use the transformer to re-rank those scores to be more accurate. So that's the point of this model. So we start off by inserting the inputs, which is just the scores from the original learning to rank model. And then we add positional encoding, right? So it outputs a vector that actually gives context, right? So that's where context, the context-aware model gets its name from, which is also called embedding. And this is based on the position from the previous learning to rank algorithm score. If you want to like oversimplify it, you can think of it as sort of a distance metric as well. Yeah, and then you take those positional encodings and you actually pass it to the encoder block. So here we go, and then we pass it into this block over here. Cool. So over here we have multi-head attention, and it's also based on what's called a self-attention mechanism, which constructs representations of the relevancy of each currency to one another, or each asset. And again, it outputs a vector for each of the currencies. Okay, so after we've done that, we can actually go and we can feed that to this part over here, so the feed-forward network. And how I understand it is that this is just a neural net on top of the multi-head attention. Okay, so it transforms that attention vector that we feed it into a vector that actually accounts for the interactions across currencies, because that's a problem that we had before, right? So we couldn't really account for the different distributions, right, across the features of the currencies. So this helps us with that. So after we do this, we then go on to what's called stacking. And this is what makes this transformer unique. So I'll show you guys in the next slide as well how that stacking actually happens. But basically, it just boils down to a projection onto a fully connected layer. So we project, and then at the very end of the transformer, we project onto a fully connected layer again. Yeah, and the reason we do that is just so that we can learn more complex representations. So this transformer is a very complex way of basically getting more accurate rankings. Yes.
Good. Yeah, if I can just pause on
Yes.
that. So I
Yes,
guess,
definitely.
you know, if you have to break down how this transformer architecture basically works, or what is this self-attention. So it was first used in natural language processing. So usually what they did was, if you want to complete a sentence, you would have like a recurrent neural network that takes, for example, the dog is jumping the fence. And it would start with the, and then dog, and then learn the, you know, what follows in a sequential manner. But with self-attention, those, you first start with those words in a word embedding, right? So each word is then in a vector space. I think that there's a quite nice library called Word2Vec that actually does that. And the idea is basically that all these words are related with one each other. They are aware of one another, right? So it has, for example, dog and fence has a certain relation. And mapping them into a vector space, you can use then this self-attention which works with the queries and queues and everything. And yeah, I think that's the basic idea. And then since you use this self-attention mechanism to determine the relationship to other words, then you don't necessarily have an idea of the position of these words with relation to each other. And that's why you use the positional encodings for, you know, to relate some type of position with each word. And this then just translates, in this case, they just use it on the features for the currencies.
Michal, and am I right in saying that, so the reason, because you mentioned that, so normally you use it sequentially, right? But the transformer, what makes it unique is that it runs everything in parallel, right? So
Yes,
that's a
exactly.
unique.
There's also faster to do.
Yes,
And
yes,
you don't have that problem of explosive gradients.
yes, yes, exactly. Okay, okay, cool. Yeah, thanks for adding that, Michal. Yes, that's good. And what this paper like essentially tries to represent in this graph is the original like base model that I showed you over here is basically inserted in here and then stacked on top of one another. So you'll see that over here we have the original scores, right, for each of the currencies or assets. And then after we feed that into our n stacked encoded layers, we get an output that's basically just, you know, the refined scores, which was the input and is now the output. So yeah, so you can see that, you know, this single encoder layer has sort of the same structure as the base model that I showed you guys. So we start off with the top retrieved currencies if we go long, and then provided by an initial ranking algorithm, so lambda mart, for example, and then you pass that through the fully connected layer. So over here, you feed that through the stacked encoders, right, before sending it through another fully connected layer. And how I understand this is, again, it's just a normal neural net that you pass it through. And it just helps the encoder and the decoder to give you the score that you're looking for. So over here, we just have a formula that sums all of this up. So you have your original scores and you transform that into the re-ranked scores. Okay, cool. I think, Michal, I don't know if you want to add anything. It's basically just a summary.
No, I think that explains it clearly. Yeah.
Awesome. Okay, cool. So now we get to the fun part, so the results. So as I said before, we're just going to take some of the benchmarks that we know, so a multi-layer perceptron, randomly choosing assets to long and short, and then also there's a last one. I'll get to that one. But yeah, we're just going to compare that to our learning to rank benchmarks, and we'll see, you know, who outperforms who. And for the second part, we'll look at the original learning to rank algorithms, and we'll just compare them to their context-aware counterparts. And then for the very last part, we have the normal and the risk-off market states. So they actually condition the data, you know, to account for these market states, and then we'll see if the context-aware models still outperform the rest. Okay. So first off, the normal benchmarks. So the conventional ones include just choosing assets at random. To long and short, we have the volatility normalized MACD. So that's BAS, this one over here. And then we also have the multi-layer perceptron, so MLP. Cool. And if we just look at these two for a sec, we can see that for the MLP, it outperforms the BAS when it comes to returns and also the Sharpe ratio. And yeah, the authors just give a reason for this. They're just saying that, the multi-layer perceptron is overfitting. So that's one reason that they give. But if we look at the learning to rank algorithms, so we have 4 benchmarks. So pairwise logistic regression, that's PW, this one over here. We have the list MLE, this one over there, list net, and then the lambda mot. So that one. Cool. And we can see that, the lambda mot, so same as in the previous paper, outperforms the rest when it comes to returns, and then the Sharpe ratio. So volatility, I see that just choosing assets at random, that one outperformed. But yeah, so the basic idea, returns, Sharpe ratio, and again, the lambda mot is the base one. So it's quite interesting to see the same trend in this paper as well. Cool. And then just a note, we rescale to the 15% annual target volatility. So that's what we're seeing over here. Okay, and now we can compare the original learning to rank algorithms with their context-aware counterparts. So we see that we have the 4 base models, 1, 2, 3, 4, and then we have their context-aware transformer network counterpart. So you'll see that for the pairwise logistic loss, we just add plus P. So this is the original, and then we have that one, right? So pairwise logistic loss, and then we also have the list net loss over there. And we just repeat that for each of the regionals. Okay, cool. So again, we can see that, moving from the original learning to rank model, so let's focus on the Sharpe ratio, for example, we can see that moving from that to the transformer network, right? We move from 0.6 to 0.9 and over here 0.7. So there's definitely an improvement, right, from the original to the context-aware model. And then the same for this one over here, which is the list MLE. We see that same trend. So the Sharpe ratio increases for both. And yeah, same over here for the list net. And then for the lambda mot, we can see that we go from the original model had a Sharpe ratio of 0.8, and then we jump to a Sharpe ratio that's greater than 1. And this is also the base Sharpe ratio obtained. So again, the lambda mot outperforms, but this time not the original model, but the context-aware model. So more specifically, plus L, which is the list net loss. So that's quite interesting. Cool. Michal, do you want to add something here?
So if I understand correct, the pairwise logistic loss, it works by just looking at the pairs, right? But the list looks at each item with the entire list, if I understand that correctly.
Yes. Okay. That's great. I do believe like Jock gives a very nice explanation of that in the previous paper. Yes. But yes, that's correct. Cool. Yeah, and it's interesting that lambda mot outperforms the rest.
The one thing that's interesting to highlight here, I think for me, is that we're seeing again confirmation that lambda mot is the go-to algorithm to use. And I think these Sharpe ratios look a lot more realistic, right? Like here we're seeing, a Sharpe of 0.8 on lambda mot, and then lambda mot plus L is 1.008, right? So that is a lot more realistic. I mean, I would want to still validate these returns myself by us building, for example, like lambda mot and testing it and that kind of thing. But yeah, I'm just glad to see that this paper is still showing that lambda mot is the winner, and that we're not all of a sudden now seeing, with the different universe, that the neural net type architectures are outperforming. So that's the only one added thing that I think is quite nice to see. Yeah.
Cool. Thanks so much, Doc. Awesome. Okay, so for the next slide, so this just confirms what we already said. So if we look at the pairwise loss and then also the listwise loss, right? So the orange and the green curve, we can see that we have improved returns, right? For each of the benchmark models, when you compare that to the baseline. Yeah. Okay, cool. And then this is the last part. So if we look at market states, the authors actually try to condition the data in such a way that they could, compare the normal with the risk-off market states. So that's quite cool. And again, we have our learning to rank benchmark. So the 4, 1, 2, 3, 4. And then we also have their context-aware counterparts. And we can see if we look at the long short ranking performance, right? So specifically the list net, okay? If we look at jumping from the normal to the risk off market state, that's quite a big jump. And we also have the best performance, right, for the list net in terms of the risk off market state. And we can see this in the Sharpe ratio, how the Sharpe ratio increased as well. So for the risk off market state, in terms of Sharpe ratios, the list net model actually has the highest Sharpe ratio, which is quite interesting. You know, I would expect it to be, you know, with the lambda mods, but it's actually the list net with the list net loss that got the best Sharpe ratio for the risk off market state. So that's quite interesting. And then the lambda mod, again, so we have the best long short ranking performance for the normal market state, right? So that's lambda mod. And then we can see the Sharpe ratio is actually the highest in the normal market state, but this time for, again, that list net loss. So that's quite interesting to see as well. Yes, and this is it. This is the last slide. Michael, Jock, if you want to add something, if you guys have any questions, you're welcome to ask.
Yes, I've one question on the risk off, right? So I think in the paper they mentioned that when the VIX is 5 points higher than its rolling 60-day moving average, do they then separate those? You know, those periods are kind of in between, right? So how do they actually separate those normal and risk off?
Oh, I saw that, and it said that the risk off periods only account for 4% of the data or something, right?
Yes, yeah.
Yes. I'm actually not sure how they do that, Nicole.
Okay. No, it's only, you know, if it's only 4%, how can they make? I don't know. It seems like a small sample.
Yes.
To test it on, even though I mean, with the data is almost 20 years, I believe.
Yes, 2000 up until 2020. Yes.
Okay, well, that's interesting.
Yeah, and it's interesting, like, to see that you know, for the risk off period, it's actually the list net that outperforms and not the lambda mod. So that's very interesting. And not only do you improve your ranking accuracy on average, but also for normal and risk off market states when you include the context aware model. So that's also cool to see. Cool. And that's it.